folks. Welcome to CSE 1322. This is module number 4, part 2. And today we're going to talk about recursion. This is definitely a topic that's going to take you a minute to understand. And I promise you that most things that you've done in this class up until now have usually come fairly intuitively. Unfortunately, this is a topic which to most people is going to be non-intuitive at first. I promise you that this is a really important topic. We're not just teaching you this because it's fun to teach or because it's some theoretical abstract thing that everybody should know. It really is something you will use in your code, and it's something that all computer science people must understand. So it's very important that you understand this, but I want you to know up front that it won't come easy. This is going to be a very different way of thinking, and at first you're going to watch what I do and it's going to make a lot of sense, but when you sit down and try to code it, you're going to struggle with this. It just takes a lot of practice, and once you do it for a while, it's going to start making sense. So we're going to begin today's lecture with a math problem, strangely. The question is, if I were to ask you about factorial, which is a mathematical formula, how do we go about calculating? So on the slide, we have 6 factorial. And I'm actually just going to do this on the board for a while. I'm going to go ahead and kill the PowerPoint presentation just so that it's a little bit clearer for a second here. All right, so 6 factorial mathematically is equal to 6 times 5 times 4 times 3 times 2 times 1. That's how you calculate a factorial. If you're wondering why factorial exists, there's a lot of probabilities that have to do with factorial. For example, if I have a bag that has 6 balls in the bag, and I ask you to reach into the bag and pull out 1 ball, what are the odds that you're going to, what's the probability of you finding a particular ball in that bag? Well, when you reach in to pull out the first ball, there were 6 choices in the bag. Once you've taken that out and you reach in again, there are now 5 balls in the bag. And once you reach in, there are 4, and then 3, and then 2. So the most number of ways that you can organize the balls or pick the balls out of the bag in any order is what's called 6 factorial. So this number is calculated by multiplying 6 by 5 times 4 by 3 by 2 by 1. Likewise, if I were to ask you what is 5 factorial, well, it works the same way. It's 5 times 4 times 3 times 2 times 1. And any number works out the same way. So, for example, if I asked you for 1 factorial, well, it's just 1, because it's 1. There's only one way that you can arrange 1 ball. 2 factorial will be 2 times 1, which is 2, because there's 2 ways. These numbers grow very quickly, by the way. So 1 factorial, as I mentioned, is 1. 2 factorial is 2. 3 factorial is 6, because it's 3 times 2. And 4 factorial is going to be 24, because it's 6 times 4, which is 24. 5 factorial is going to be 5 times 24, so it's over 100. So you can see this is growing very, very quickly. Okay, so there's a couple of things you could notice if you stare at this for a few moments. So I told you that 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And then up here, I gave you 6 factorial, which is equal to 6 times 5 times 4 times 3 times 2 times 1. So you might notice that this part of the equation is the same in both of these cases. 5 times 4 times 3 times 2 times 1. So another way that you could write 6 factorial would be 6 factorial is equal to 6 times 5 factorial, because this was 5 factorial, and that fits in there. That's interesting. It's kind of odd, but it's interesting. So you might say, well, okay, so wait a minute, is that generally true? So what happens if I ask you for 9 factorial? Well, 9 factorial indeed is equal to 9 times 8 factorial. And 8 factorial is really equal to 8 times 7 factorial. As a matter of fact, 7 factorial is equal to 7 times 6 factorial, and so on and so forth, all the way down to 1 factorial, which, as I mentioned before, is just equal to 1. So it seems like after you've looked at this for a few moments, you could realize that there's a pattern here. So the factorial of any number, if I extract it out, so n factorial is simply equal to n times n minus 1 factorial. Now, this is called a recursive definition. It has nothing to do with computer science yet, we're just talking math here. But effectively what I'm telling you is that if you want to calculate what n factorial is, you just have to multiply n, which you already know, by n minus 1 factorial, which you probably don't already know. But you can answer what n minus 1 factorial is by looking at the next number down on the list, which will bring you to the next number, which will bring you to the next number. And eventually, no matter what n you start with, you'll eventually end up down at this base condition, which is that 1 factorial is equal to 1. So, for example, if I ask you what is 2 factorial, according to our n definition, it's equal to 2 times 1 factorial. And it turns out that I already know what the answer to 1 factorial is, that's just 1. And so once I cross it out and put a 1 there, I get that the answer is 2. And likewise, if I had started off asking you for 3 factorial, I know that that's equal to 3 times 2 factorial. Well, I now know that 2 factorial is equal to 2, so I can just cross that out, and I now know that the answer is 6. And if I go a step beyond that, 4 factorial is equal to 4 times whatever 3 factorial was, which is 6, so 24, and so on and so forth. So the definition of factorial is answerable as long as you know what the answer is to the previous question. Or to phrase this in a different way, there is a base condition which is true for factorial, which is that the factorial of 1 is 1. And eventually, if you work your way down to that base condition, you can solve any factorial by simply calling the factorial of the number before you and figuring that out first. So if I want the factorial of 65, I must first figure out the factorial of 64. Once I have that, it's very easy to give you the answer to the factorial of 65. And likewise, if I want the factorial of 64, I must first figure out the factorial of 63. Then I know it's easy to calculate the factorial of 64. And I keep doing that until eventually I ask myself the question, well, in order to calculate the factorial of 2, I need to know the factorial of 1. And then I go, aha, I know the answer to that is 1, because that's a definition. Now I can answer any question. This is a recursive problem. The answer to any particular question with factorial requires you to know the answer to the previous version or a slightly smaller version of itself. The factorial of 64 uses the factorial of 63. The factorial of 7 uses the factorial of 6, which in turn uses the factorial of 5, which in turn uses the factorial of 4, and so on and so forth. All right, so let's go back to our slides real quick. So in our slides, we had started. Factorial of 6 is equal to 5, 4, 3, 2, 1, as we said before. Factorial of 75 would be 75 times the factorial of 74. This is recursive. You need to figure out the factorial of 74, which is the factorial of 74. Sorry, it is 74 times the factorial of 73, which means you need to find out 73, which means you need to eventually get down to 1. So the definition of recursion is when you have a method that calls itself. They're very easy to identify because you've probably never done this, or if you did, your code most likely crashed. But it is possible while you're writing a method to call that method itself. And it will create a clone of that same method, which it will then go off and answer the problem. In order to make anything recursive, you need 3 things. You need a recursive call, you need a terminating condition, which is how you know that you're done, and you need to make sure that each of your recursive calls is getting you closer to the answer. So in the example of factorial, the terminating condition is the factorial of 1, because by definition, the answer is 1. The recursive calls are, to get to the factorial of 72, you need the factorial of 71. That's the recursive call. You're calling factorial while you're in the middle of writing factorial. Okay, so a recursive problem works like this. If you're asked the simplest problem, which is what is the factorial of 1, then you just give it the answer. If you're asked a more complex problem, then you just move yourself closer to the simple problem, and eventually you will get there. All right, so first determine your base case, which is when you're going to stop, and then determine how you're going to get close to it. So as we said, in this example, the base case is you're going to have factorial of 1. We know how to answer that. And it could also be factorial of 0, because by definition, factorial of 0 is also 1. That's just a mathematical property. And your recursive call is going to be that you call yourself and you multiply the current number by the factorial of the previous number. So let's write this out in code. We have public int factorial, which takes in an integer n. So if I want the factorial of 10, int n is going to be 10. I'm going to do this code in IntelliJ. So we have public, are we doing an int or are we doing an int? We are. All right, public int factorial, and we're taking in int n. All right, so the first thing that we're going to do is we're going to say, if the n that you gave me is equal to 1, then I know the answer, return 1. So if n is equal to 1, I return 1. Very simple. If you ask for the factorial of 1, I know that the answer is 1. So we're just going to check this down here in our main. I'm going to make a call to my method. So I'm going to say int answer is equal to factorial of 1. Let's see what we get. We'll print that out. Print out the answer. What's it upset about? Non-static method. Oh, it has to be static. I'm in main, so I have to put static there. Great. We're going to run it, and it should say the answer is 1. Missing a return statement. 0 outside the if statement. It's complaining because the only return was in an if, which may not happen. So great. Hit run, and we get 1. So if I ask for the factorial of 1, it gives me 1. So far, nothing recursive. All of that's just basic code. Here's the magic. If you ask for anything that is not 1, then I'm going to return n times the factorial of n minus 1. So if you ask for 1, the answer is 1. That's easy. But if you ask for anything else, then I'm going to tell you that the answer is n, whatever you gave me, times the factorial of n minus 1. The n minus 1 is because factorial of 75 is equal to 75 times the factorial of 74. That's where I'm doing the n minus 1. Now, this is the part that's going to melt your brain. That right there is a call to a method. And the method that it's calling is the method that I'm actually currently writing. I am calling myself in the middle of a method. That is what makes this method recursive. And that's the part that's really hard to get your brain around. But I promise you nothing magical has happened and nothing is different between what we did in the previous slide deck when I showed you a call to method 1 and a call to method 2. Exactly the same things are happening here. It's just that the method that I'm calling isn't method 2 from method 1, it's factorial from factorial. Once you get over that detail, this actually makes a whole lot of sense. All right, so I'm going to print out what is the factorial of 5. So I'm changing my question to factorial of 5 down here, and I'm going to run it, and it tells me the answer is 120. And I can think about that for just a moment. I know that the factorial of 4 was equal to 24. That's what I wrote on the board, right? Factorial of 4 was 24? Yeah, I believe so. Well, let's find out. Let's not get this wrong in the video. Factorial of 4 is indeed 24. And if you multiply 24 by 5, you get 120. Because 5 4s are 20, and then the rest. So 120. So this somehow seems to work, but it doesn't have a loop in it. There's no point where I'm telling it to add 1 to any, like I'm just calling myself. And that's the part that's really very confusing. I said that the factorial of any number is equal to that number times the factorial of one less number. So how does this work? Well, let's go back over to the slides. And this is the same exact code. They didn't bother to put this in an else because the only possibility, if this if happens, the return ends the method. Otherwise, the return continues on. So they didn't bother to put this into an else, but it's the same code. All right, so let's trace this code. This time we put it back in an else. All right, so we're going to build our function stack, and we're going to start off doing factorial of 4 from main. So we start off in main, and we begin with this first line of code. We're told to call factorial of 4. All right, so here's our call to factorial of 4, and I abbreviated this to fact instead of factorial, but it's factorial. And at this point, n is equal to 4. So I noted the 4 here in parentheses because that's how it was called. All right, so inside of this method, we're going to do all of this method until it's finished. Then we'll go back to main, all right? So we start off and we print out n. Well, that gives me a 4. Then we're going to say, if n is equal to 1, well, 4 is not equal to 1, so we're going to go to the else. The else says the result is equal to n times the factorial of n minus 1. So I'm just going to write that in here down in my little activation stack. Result is equal to 4, and that's because n is 4, times the factorial of n minus 1, which is 3. Okay, and then this is where the magic happens. It can't answer this equation. I can't tell you what the answer to 4 times factorial of 3 is because I don't know what factorial of 3 is. I have to go calculate the factorial of 3. So what's going to happen is that this version and all of the remaining code in here is going to go to sleep. And we're going to start a whole new version of factorial, but this time we were passed the number 3. That's the part that's a little confusing. I want you to think about this as if it's a whole other method. It happens to have the same name, it happens to be the same code, but don't think about that. You're just calling a method, and the method happens to be called factorial, and you're passing it a 3. As soon as you only think about it like that, it's actually not that difficult. So when n equals 3 comes in here, we print out the n, there's your 3, and we check is 3 equal to 1? Well, 3 is not equal to 1, so we go down to the bottom and we say, well, okay, then the result is going to be equal to 3 times the factorial of 2. So we're going to write that in the box because we don't know how to answer that question right now. In order to answer that question, I have to figure out what the factorial of 2 is. So all of that is still pending work, and we're going to leave that asleep for now, and we're going to call a whole new method which happens to be called factorial, to which we're going to pass the number 2. So factorial 2 wakes up, and the first thing it's told to do is to print out a 2, and then it says, is 2 equal to 1? No, it's not. So it's going to write down the result is equal to 2 times the factorial of 1. And again, that has a whole bunch of pending work, and we don't know how to answer that until we answer what is factorial of 1. And I know in your brain you're like, I know what the factorial of 1 is, we can skip. No, you can't. The computer doesn't skip it. It doesn't understand what factorial of 1 is inherently. It has to call the factorial method to get to that answer. So all of this goes to sleep, and we call a whole new function, which happens to be called factorial, and we're going to pass it a 1. So factorial of 1 gets called, it prints out the 1, and it says if 1 is equal to 1, which it is, then it returns 1. Okay, now, what has happened here is that the recursion has stopped. Notice that in this version, we didn't call ourselves again. If we did call ourselves again, we'd have a problem, because we've reached the one thing that is a fact, which is the factorial of 1 is 1. That's a fact. It's not something I have to calculate by figuring out some other thing. I just know the factorial of 1 is 1. So I'm returning 1. Okay, so now what's going to happen is, in our activation stack, over on the left here, we have, why does things not work? Turn on, there we go. Over in our activation stack, we are currently on this method, and it just decided that the answer is to return 1. It didn't return some functional call or call to another method, it simply said return 1. Since it returns 1, this was the original thing that called it on the previous layer of the activation stack. So that 1 is going to get plugged in here, and effectively the answer to factorial of 1 is simply now 1. Well, now this version is going to wake up. This version is done because it returned 1, which was its job. So when this version wakes up, it says, okay, I went to sleep right at a call to factorial of 1, but now my statement reads result equals 2 times 1. Well, I know the answer to that question, it's 2. So it now says return 2. That 2 is going to get filled in to the previous layer of the activation stack because this layer is now done, and this just becomes 2. So 2 times 3 is equal to 6. And again, this is now done, and that 6 gets filled in here, and so 6 times 4 is 24, and that's done, and it gets filled in here. And again, we're down to this print statement at the very bottom, which is going to print out 24. So that's the preview of what's going to happen. Let's actually watch it happen. So we are just in the version of factorial that was called with 1. It just said if 1 is equal to 1, which it is, return 1. So that return 1 is now going to finish off this call to factorial. Once you hit a return statement, the method ends. That's a rule. You cannot proceed to any more code once you've hit a return. A return statement immediately ends the code. And if the return statement has a value after it, it returns that value. So this was told to return 1. Who does it return to? Well, it returns to the previous layer in the activation stack, which had previously asked the question, result equals 2 times factorial of 1. Well, factorial of 1 was equal to 1. We just found that out. So now its line reads, result equals 2 times 1. It can answer that question. That answer is 2, so it prints out a 2, and it returns 2, because that's what it's told to do. When it hits a return statement, that part of the activation stack is done, and a 2 is plugged into the previous layer of the activation stack where we had a call to factorial of 2. So that layer now reads, result equals 3 times 2, which is 6. And then we're going to pop that off the stack. That's going to make it a call to the previous version where the 6 is going to get filled in. That 6 is going to print out. 6 times 4 is 24. And then we're going to print the result. Or sorry, return the result of 24, which is going to print at the very bottom. Okay, so the activation stack that I drew here is not some theoretical thing that we make you do because we enjoy making you do things. It's literally how you will solve any recursive problem. We're going to give you questions like this on tests, where we're going to have a recursive call, and we're going to ask you what is the value that you get at the end of it. The only way to solve that problem is not to look at it and say, well, it's factorial, so it should just be. No, it's to look at it, draw the activation stack, and just follow the code line by line, which is exactly what the computer does. If you try to skip ahead or imagine what's going to happen in the future or try to skip a step, that's where you're going to get into trouble. Turn off your brain, read each line of code, and do exactly what that line of code tells you to do, because that is all the computer is doing. I promise you there is zero magic going on in this code. It is simply reading and executing every line of code exactly as it's told to do. The only thing that's weird about this code compared to every other piece of code you've looked at is that this code happens to have a line where it magically calls itself. That's the only thing that's different. But if I change this to method 2, it's exactly what we had in the previous slides in the last lecture. It's just that you have a method calling another method. So if you turn your brain off and you execute the code line by line and you keep track of it all in an activation stack, you will end up with the right answer. If you try to guess, you'll probably end up with the wrong answer, because this is hard to trace without an activation stack. And what I mean by that is, even me, who has been doing this for many, many, many years that I don't want to give you a number on, will draw an activation stack when I'm tracing recursion. If you come to my office hours and say, I don't understand recursion, I need help to figure out what this code outputs, what I'm going to do is I'm going to pick up a marker and I'm going to draw on the whiteboard an activation stack, and I'm going to have you read it to me line by line, and we're going to just do exactly what it tells us to do. And if you follow that, you will get the correct answer. That is the only way to trace recursive code, is just turn off your brain and do what the code tells you to do. That's exactly what the computer is doing. It doesn't think ahead and say, oh, I think I know the answer. No, it doesn't. It just follows the code. Okay, so if you are writing code that is recursive, what are the common mistakes you're going to make? Well, you're either going to omit the base case, or you're going to write a recursive step that doesn't move you towards the base case. Those are generally the two problems. Either of those is going to produce the equivalent of an infinite loop. Okay, so let's take our factorial code. This is, again, the same code that we had before. We're calling factorial with n-1 and multiplying it by n, and that's great. I'm going to change my 5 down here to a much bigger number, like 15. And we're going to run the code. And wow, that got big really, really quickly. So the factorial of 15, you're already in 2 billion. As a matter of fact, any number greater than 15, you're going to quickly exceed the size that an integer can hold. You're going to have to start using longs. So factorial grows really, really fast. This code executed really quickly. But if I could ask it to show me the activation stack, there were actually 16 calls on the activation stack. There was main, and then there was call 1, 2, 3, 4, 5, all the way up. Or more specifically, factorial of 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and then eventually factorial of 1. And then and only then did it start collapsing back down again as it got the answer to factorial of 1 at the top. So the same thing happened here, it just took longer, and it would take you a little bit longer to trace it if you change that. All right, so let me change this back to 4, and let me change my code a little bit. I'm going to take out this if statement completely, and I'm simply just going to say return n times the factorial of n-1. So all I did was I took out the if statement. I'm going to run it, and we're going to see what it outputs. Well, what it output was Java puked in a really horrible way. And I'm having to scroll here really far away because it's just saying at main factorial main Java 6, at main factorial main Java 6. As a matter of fact, if I move this little window and I take my scroll and I go all the way to the top, ultimately it said, exception in thread main language Java, stack overflow error. At main Java, at main Java, at main Java, blah, blah, blah. It's always telling me it happened at line 6, which makes sense because that's this line. So what actually happened here? Well, if I were to trace this code, I'll do it over on the board here real quick, so I'm going to leave the share up. But effectively what is happening is you start off with your activation stack and you are asked for factorial of 4. But since there's no terminating condition, that if statement that used to be there, it does the main, which is calling factorial of 4. And then I'm just going to stop the screen share so that you can see this in a little bit bigger of a window. There we go. It did factorial of 4, which made a call to factorial of 4. Well, that said, okay, return 4 times factorial of 3. Great. Factorial of 3. Everything seems like it's working correctly so far. It says return 3 times the factorial of 2, which is going to make a call to factorial of 2, which says return 2 times the factorial of 1, and then you have factorial of 1. Okay, now here's where things go off the rails. Because I took out the if statement, it doesn't just return 1. It returns the other part, which is the return 1 times the factorial of 0. Okay, not so bad. That makes a new call to factorial of 0, and that tries to return 0 times the factorial of -1. Okay, factorial of -1, that's going to give you return -1 times the factorial of -2. And I think you can start to see what's going to happen. -3, -4, -5, -6, -7, -8, -9, 10, 11, 12, 13. And we're going to keep going. And much like my whiteboard, it's eventually just going to run out of room. And you might say, well, how does a computer run out of whiteboard? Well, your computer has got a certain amount of memory in it. And that memory is fixed. you purchased it with a certain amount of RAM. When you bought your computer, your laptop, you might have bought 8 gigs of RAM or 16 gigs of RAM, or maybe you were fancy and got 32 gigs. Whatever number you got, that's how much memory you have. And each one of these calls is occupying a small amount of that memory. And so there's a limit as to how far you can go with this stack, which is you will run your machine out of memory. Because there's nothing in this code that's ever going to stop it. It's just going to keep going. And so literally what happened is that went chug, 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 -2, -3, -4, -7, -100, -10,000, -15,000, -30,000. And eventually, Java literally had no more memory left in its stack. And that's the error that you got. You got a stack, we call this the activation stack, overflow error. It ran out of stack space. And so the reason that happened is because you don't have a terminating condition. You have nothing that's telling Java to stop. It just keeps going and going and going until you get to no more memory. So the solution to that is the if statement that made it actually stop. So if n equals 1, return 1. Now it actually will stop when it gets there. So a very important lesson is that with recursion, you always have to know what your terminating condition is, what the moment is that you're going to stop making these recursive calls. So every recursive method that you write, no matter what it is that you're solving, is going to have a terminating condition, which is going to specify what happens in the most base case. It's also going to have a recursive call, which is where you call yourself. That's what makes it recursive. And then finally, that recursive call has to be moving you towards the base case. If the recursive call isn't moving you towards the base case, let's say I take away this -1, then now we've got a new problem. Return n times the factorial of n. Well, if I call this with 4, on the first call, that's going to be 4 times the factorial of 4, which is going to be 4 times the factorial of 4, which is going to be 4 times the factorial of 4, which is going to be 4 times the factorial of 4. And again, I've run myself out of stack space. This is not moving towards this terminating condition because the n is never changing. So what I'm telling you is that if you are asked to write a recursive method, really you just have to figure out 3 things. What is the terminating condition? And then you're going to have an if statement. Could be a case statement, but it's usually an if statement. And then what's your recursive call? And how do you make it so that your recursive call is getting closer to your terminating condition? That's red -1 in here. Those are the 3 things you've got to answer. And if you answer them correctly, then you're going to be able to write recursive code that works. I will point out that you can have this same problem sort of with a loop. In a loop, you can have something that runs forever, and it's called an infinite loop. Like, for example, you could say for int I equals 0, I greater than -1, I plus plus. Well, that's always true. Every number that it's going to do is going to be valid, and that's always going to be positive. Eventually, you'll overflow an integer, and it might stop, but otherwise, it's just going to run forever. So the same thing can happen with recursion. It's just that with recursion, your program is going to crash. And this is part of the reason why recursion is difficult for students. Up until now, nothing that you've written should have crashed Java. If you wrote a loop that kept going forever, well, it just kept going forever. Java just kept running and life was good. The only time that you really saw errors was when you made syntax errors and the compiler was directly able to tell you what you had done wrong, missing semicolon on line 8. But now you're going to be writing code where syntactically it's correct. Whether you put that if statement in there or not, it's completely valid. But logically, it doesn't work. And the problem is going to happen in runtime. So it's going to compile, it's going to start running, and then it's just going to crash because it runs out of stack space. So that's very different than having a loop that runs forever. And it's disheartening to see it happen when you're a coder, because you're like, I tried, I did all the right things, and yet you're still crashing on me, and I don't know why. All right, so to avoid Stack Overflow problems, you're going to try not to recurse too many times. Generally, that's because you have forgotten your terminating condition, or you're not moving closer to your terminating condition with each recursive call. But it is also possible that you can overflow the stack when you wrote correct code. So let me explain that for just a moment. This code is correct. If I ask for the factorial of 4, it happily spits back out that the answer is 24. If I ask for the factorial of 6, it happily spits out that the answer is 720. Life is good. Let me ask for the factorial of 600. I've changed none of the code, but all of a sudden it returns 0. Well, why? Okay, so one of two things happened there. Most likely what happened is that I overran an integer. The size of that number, the factorial of 600, is huge. 600 times 500 times, 600 times 599 times 598 times 597. Each time you're multiplying by 600, or a number very close to it. Of course, that number gets really, really large really quickly. So most likely the reason I got a 0 here is because I overflowed an integer. But let me put in a much bigger number. And now I didn't get a 0. The program actually crashed. There's nothing wrong with this code. It is all 100% syntactically correct. But it crashed. And the reason it crashed is because there's just not enough memory in my machine to answer this question. That's quite literally the issue. Now, I could have written factorial with a loop. You absolutely can calculate this exact same thing with a loop, and you will get the same answer. And in a loop, I will be able to calculate the factorial of 600,000 or 6 million or whatever number that is. And it will work as long as I don't overflow an integer. If I store it in a long, it'll certainly work. So what am I telling you? I'm telling you that sometimes sometimes recursion is going to make it so that you overflow the stack even though you did everything correctly. Generally, for the questions we're going to ask you in this class, if you are overflowing the stack, it's because you made a mistake. You either forgot the terminating condition or your recursive call is not moving you closer to the winning solution, as it were. But it is possible that you run over the stack because you simply just run out of memory. And this proves that factorial is not really the most efficient way to do things sometimes. So in most cases, for the very simple examples that we're going to do for the next week or two, almost all of them you could answer them also with a loop, and you would get an answer that is faster, more efficient, and you probably should have really written it with a loop. Honestly, if you're writing factorial as code, first off, you should just use the built-in one. But ignoring that, assuming that you're going to write it from scratch, honestly, you would be more efficient to write it with a loop. So why are we showing you how to do it recursively? Because there are a class of problems that are much, much harder with a loop than they are with recursion. They're hard for us to start with those problems because you have to build up to it. So trust us, the way that we're walking you through it. We're going to have you do a whole bunch of problems that honestly you'd be better off doing with a loop. But right now we're going to make you do them recursively so that you can start thinking recursively. By the end of next week, we're going to start showing you problems that you really cannot solve with a loop. There is a whole class of problems, especially in data structures, where recursion is honestly the best way to solve the problem. That's why it's so important that you understand how recursion works, because there are problems where you need it. Generally, they're going to be nonlinear problems is the term that you're going to hear, which means they're problems that don't have only one path. An example of nonlinear problems, solving computer games. So chess. At every moment in a chessboard, there's thousands of different ways that you can move. And each one of those leads to a whole new game that's different. Recursion is excellent for solving those kinds of problems. Mapping problems like Apple Maps or Google Maps, all of those problems involve you have a source and a destination and you want to find the best path between them. Doing that recursively is the best solution because at each point, when you go out onto a road, you could turn left, right, or go straight, and each of those has a whole set of problems past them that you're going to need. Those problems are best solved with recursion. So we'll get to them eventually. Bear with us as we do more simple problems to get you thinking about it. So your next challenge is we want to write a recursive process for the following: x to the power of y. You can assume that x and y are both positive integers. So what I want you to do is I want you to start thinking about how you would solve this problem. So I'm going to go ahead and begin coding it. Hopefully you're going to pause the video and you're going to think about it for just a moment before you watch what my final solution comes out to here. So I'm going to call this int. It's going to return an int, public static int, and I'm going to call it power because it's calculating the power. I'm going to take in an x and I'm going to take in a y, and this is going to be recursive. So the first question that you have to ask yourself to solve this is, what is the base condition? What is the condition for any power question that I already know the answer to? So 2 to the third power is not something that most people know off the top of their head. It's 8. 2 times 2 times 2, that's what 2 to the third power is. 2 to the fourth power is going to be 16. So at each point, what I'm doing is, in my head, I'm multiplying the first number by itself as many times as the second number tells me to. So I can immediately think about how I would do this in a loop. For int I equals 0, I less than y, I plus plus, answer equals answer times x, and just start off the answer as 1. Will be the looping version of it, return answer. I multiply the answer by x each time through until I get to, I do it as many times as y tells me to do it. So let's check that. So we're going to do power, we're going to do 2 to the third power. We should get 8 if we did that correctly. First off, we need a semicolon here, and then we're going to run it again, and sure enough, we get 8. All right, and then just checking it again, 2 to the fourth power, and that should give me 16 because we're multiplying 8 by 2. Great. So now, that's a looping solution to the problem, or an iterative solution to the problem. That is not what we were asked to write. What we were asked to write is a recursive solution to the problem. So step 1 with recursion is always to figure out the base case. So what's the simplest question that you can be asked? And I'll tell you that in general, when you're trying to figure this out, it's probably going to be that one of the numbers that you got is either a really small number or a really big number. So let's start off with the y. Let's talk about the y. The y is telling me how many times I need to do something. So what happens if the y is 0? What happens if I ask you for 2 to the 0th power? Well, I believe there's a definition for that. 2 to the 0th power is 1. As a matter of fact, no matter what you ask for to the 0th power, the answer is 1. 77 to the 0th power is 1. That's just a mathematical definition. So if y is equal to 0, you're going to return 1. That's your base condition. That tells you that they asked for something to the 0th power, so life is good. In all other cases, we're going to have to figure out our recursive call. So the second step that you're going to do is you're going to figure out your recursive call. I'm going to have to call power. That's what makes something a recursive call. And I'm going to have to pass it 2 parameters because power takes in 2 parameters. Just like it always has in everything we've done before recursion, I still have to match. I have to send it 2 integers. So logically, if I think about this, what I'm doing is I'm taking whatever the number is and I'm multiplying it by itself. So I'm taking the x value and I multiply it by the power of x and y, but the y needs to become 1 less because I've already done it 1 more time. So this is my first guess. So I'm going to return x times the power of x and y minus 1. And we're going to pass it 2 to the 0, and that should return 1, which it does. And then we're going to do 2 squared, and that should return 4, which it does. And then we're going to do 2 cubed, and that should return 8. It looks like it does. And 2 to the 4th, that returns 16. So this appears to work. So I want you to think about how I just solved that problem. I didn't get bogged down in the details of, oh, this is hard and complicated. I just started off trying to ask some very basic questions. What is the base condition? What is the simplest case that I always know the answer to? And again, it's going to be the high end or the low end. And in this case, for power, it's going to be the low end. It's going to be something to the 0th power. That's how I got to there. So y to the 0 power, or sorry, y equal to 0 tells me my answer is 1. That's step 1. Step 2, I know I have to have a recursive call. So go ahead and put in power and parentheses and realize you need to send it 2 numbers. Now you got to figure out what those 2 numbers are. The x never changes. So in this mathematical formula, I'm multiplying the x by itself over and over again. That's how I got to x times, just like we had with the factorial one. And I have to pass an x and a y of some form, so the x never changes, so therefore I just passed x through. The y, I decided to make it one less for two reasons. One of the two numbers has to change in the recursive call, otherwise you have infinite recursion. If you're not changing one of the numbers, you're definitely going to have infinite recursion. The second thing is the number you do change must be the one you're checking in the terminating condition. So I know that the y had to change simply because my terminating condition was checking the y. So I knew the y had to change, and specifically I know the y has to get smaller because eventually the y has to hit 0. And that's how I got to the solution. So here's a very simple version of it as well. This solves it ever so slightly differently. In this case, the terminating condition that they used was if y is equal to 1, return x. And that's because any number to the first power is just equal to that number itself. So 7 to the first power is 7, 19 to the first power is 19. That's the same as x to the 0 power equals 1. Now you might say, why is it that either of these works? Well, because if the y is changing each time through on the recursive call, eventually you'll hit 1, and if that doesn't stop you, you'll eventually hit 0. So you can actually use either of these terminating conditions. They will both work. In this case, in the code, they decided to use y equals 1. I decided to use y equals 0. And then down here, we have the else return x times power of x, y minus 1. Exactly the same as what I wrote in my code. All right, so let's take another example of something that's recursive, and let's try to figure out what this is going to print. Okay, so in this case, we're giving you the code, and we're asking you to tell us what this is going to actually print out. So if n is if n is greater than 0, you're going to print out the n followed by a space. Then you're going to make a recursive call to n minus 1, and then you're going to print out the n followed by a space. That's what this code says to do. And it's being called with print numbers 10. So let's begin, and let's see what we get with this code. So I'm going to cancel the screen share, and I'm just going to write this up on the board so that you can see. And so I need to refresh my memory on the code. If n is greater than 0, print out n plus a space. All right. Okay, so if n is greater than 0, you're printing out, I'm just going to write print, the n plus a space. And then there's a recursive call. This method is public static void, I think. I've forgotten the code. Public static void print numbers int n. Great. Okay, so it prints out that. Then we have a recursive call, print numbers n minus 1. And then we have a print statement for n and a space again. Each of those have semicolons. That's a curly brace, that's a curly brace, and that's a curly brace. And I think that's what we got. All right, so let's start tracing this. And again, I don't care who you are, and I don't care how long you have been looking at recursive code. You're going to draw an activation stack, and you're going to just trace it line by line. So here's my happy little activation stack. And we're going to start off down at the bottom in main. And in main, we're going to call print numbers 10. Okay, so we begin. On the first line here, we have a call to print numbers. I'm going to abbreviate it to PN just because it's a lot of writing. So print numbers, and I passed it 10. So in this case, n is equal to 10. I'm just going to write that in here so that I remember. That's what came in as my parameter n. So it says if n is greater than 0. Well, 10 is greater than 0. So it tells me I have to do three things. I'm going to do a print of n. I'm going to do a print numbers of n minus 1, which is going to be 9. and then I'm going to do a print of n again. All right, so let's do our print of n. Well, that's going to print out the number 10. All right, no problem. Done. Now I'm going to make a recursive call to print numbers, but this time I'm going to pass it the number 9. Okay, so that's going to pop a new thing on the stack, Pn of 9, and this time n is equal to 9, because that's what we passed when we passed to the parameter. All right, so that does a print, which is going to print out a 9, and that's done. Then it's going to call print numbers with 8. So let's go ahead and do that. There's also a print down below that we'll come back to that's going to print out n again, because again, there's 3 lines of code. So I'm checking off the fact of what I've done. I did my call to print numbers here. And so my print numbers on this version is now calling print numbers of 8. Okay, so in this version, n is equal to 8. I have a print, then I have a print numbers to 7, and then I have a print. That's what the 3 lines of code are. So that's going to print out an 8 in a space. Done. And then I'm going to call print number 7. Okay, so I think you see the pattern of what's happening here. N is equal to 7. I have my print numbers to 6, and I have a print. Okay, so that prints out as 7, and I call print numbers of 6. All right, n is equal to 6 this time. We're doing a print. This is continuing on the same line. I've just run out of space. So there's a 6. I call my print number with 5, and then I have a print. All right, so I print out my 6. I call print numbers 5. N is equal to 5. Print the 5. That's done. Call print numbers of 4. Then there's a print underneath it. All right, so print numbers of 4. N is equal to 4. I'm going to do a print. Here's my 4. I'm going to do Pn of 3. That's a 3. And then I'm going to do a print again at the end. All right, so Pn of 3, looking good. N is equal to 3. We're going to do a print. That gives me a 3. We're going to call print numbers of 2. And then we're going to do a print. Yeah. Okay, so Pn of 2. N is equal to 2. We're going to do a print. We're going to call print numbers with 1, and we're going to do a print. Okay, so print the 2, call print numbers of 1. All right, so n is equal to 1. I'm going to do a print. Here's the 1. I'm going to call print numbers 0, and then I'm going to do a print. All right, now don't shortcut this. You're just going to keep going. So that calls print num of 0. All right, n is equal to 0. Okay, so let's go back to reading the code. In each of these cases, the exact same thing happens. But for the first time, something different is going to happen when n is equal to 0. So it says, if 0 is greater than 0, which it is not. 0 is not greater than 0. So since that's not true, it continues on after the print statement, which the next line after the print statement is this closing curly brace down at the bottom. So really what this says is end. There's no return. The code just ended. We ran to the end of the method and it's done. So this 0 just dies and it pops off the stack. All right, and so once it dies, I'm actually going to erase it just to make the stack clearer. Pn of 0 is done and over with. And now we're back at Pn of 1. So this code wakes back up and it's already done the print statement. It's already done the Pn of 0. So now it moves on to the next statement, which is to print n again. So it's going to print another 1. Okay, and now it reaches this closing curly brace because it was in this if in this version. It did this, it did this, it did this, now it's here. And then it moves on to here, and that's a closing curly brace, and we're at the end of a method. So this method is done, and it pops off the stack. And that's done. Okay, well now the top of the stack is this method, and it wakes up, it's done a print, it's done a call to print numbers of 1, and now it has told to be printing out 2, or print out its n again, so it prints out a 2. and then it's done, and it's done. So it pops off the stack. And you'll notice this is a pattern that happens in all recursion. You go up and up and up and up and up, and you keep adding stuff to the stack, then you hit the terminating condition, and you start working your way back down the stack again. All right, so in this version, we wake up, we've done the print num2, so now we print again, which is 3. It pops off the stack. And it's gone. All right, so this one wakes up. It's told to print out its 4. It pops off the stack. This one wakes up, it's told to print its 5. It pops off the stack. This one wakes up, it's told to print its 6. It pops off the stack. This one wakes up, it's told to print its 7. It pops off the stack. And at each point when I'm doing this, notice that each one of these are little self-contained universes. They all have an n, and the n is different in each version. But in this version, the n is 8. So when it's told to print n, it prints 8, because that's all it knows. It only knows about the variables in its little universe. So it pops off the stack. Next guy wakes up, he prints 9, he pops off the stack. Next guy wakes up, he prints 10, and he pops off the stack. And now we're back in main. This is done, so it moves on to whatever the next line of code is in main, and continues doing that until main exits. So the answer to this question, which originally was, what does print num10 give you, is it gives you 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are all on a single line. I just ran out of space because I planned poorly. But you'll notice that the numbers went down until they reached 0. They never printed 0, and then they went back up again. This is not what you probably would have guessed looking at this code. I'll remind you that this is the code that produced that output. This code simply says, if the number is greater than 0, print the number, make a recursive call, and print the number. So there's nowhere in here where I'm printing an n-1 or an n+1. The only thing I'm doing is I'm calling it with n-1. So it's a bit confusing as to why the numbers went down, and then they started going back up again. And if you remember from how that happened, the numbers were going down as long as we were adding new things onto the stack. They started going up when we started pulling things back off the stack. And that's because anything that happens before the recursive call is going to happen effectively in reverse. We started off with print nums 10, that was the first call. And so it printed 10, and then it was paused by the fact that there was a recursive call. So this never got to print the 10 again until that recursive call was complete. Well, it turned out it was going to be a whole lot of work for that recursive call to complete, because print num 10 called print num 9, and it had a whole lot of stuff that it had to do before we got back to doing 10 again. So effectively, we printed the 10, we waited for the entire program, and then we printed 10 again, which is why we have a 10 at the beginning and a 10 at the end. And likewise, for 9, it printed the 9, then it had to wait for 8, 7, 6, 5, 4, 3, 2, 1, 0. And then, when that was all complete, it printed the 9 again. So effectively, the 9 ends at the beginning and at the end. So a couple of things to notice here. Anything that happens before the recursive call ends up happening in reverse. Anything that happens after the recursive call happens in order. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 again. In this particular case, we passed in 10. So these are the ones that are decreasing, and these are the ones that are increasing. So they are the reverse of each other before and after the recursive call. So just something to be aware of when you're looking at some code. But again, if you were asked to trace this code, the correct answer is not to look at it and guess what the output is going to be. You're never going to get it right. And honestly, even if you had gotten this one right, we can make it a lot more complicated than this, and we will. What we need you to do is to actually trace the code like I did. Yes, that took a moment, but in fairness, I was explaining every line as I went. If you did it on a piece of paper, you'd be done in a couple of minutes, and you'd quickly see what happens. Do not take shortcuts and be like, okay, I see the pattern. No. Stop it. Just trace the code and see what you get. If you do it, you'll 100% get it right. Okay, so that is the end of our slide deck for section 4.2. In the next section, we're going to look at some more recursive questions, and we're going to make things a little bit more complicated and just show you more examples of recursion. I want you to take this, what we did today, And I want you to practice this. I want you to start thinking about other examples of recursion that you can do and start coding them. You're going to see some in your lab this week and in your assignment, and we're going to try and have you do a bunch of them. In the beginning, they're going to feel like you're never going to figure it out and it doesn't make sense. And then one moment, it's just going to be like, oh, that's why it works. And that's a glorious moment, but it's probably not going to happen for a week or two. So don't get disheartened. It's just going to take time, but I promise you that if you keep going, you will get there. All right, I will see you guys in the next lecture.